So actually, I've been recording these classes, and I didn't record the very first one because all I did in our very first class was I handed out the. Let me see if I can fix the microphone a little bit. Okay, can you hear me now? Is this on? Yeah. Okay. Is this on? Hello. Hello. Off, isn't it? Now is it on? Hello. This microphone's a little bit of a problem, as you can see, but I'll learn how to deal with it. Okay, so let's see. I've been recording these lectures, and so I'll have instructions for you soon on how to access them. I believe what I'm doing today would actually be called lecture number 3 because I didn't record the very first one since I was only handing out the syllabus in the agenda. And since I repeated a lot of that in the second one. Okay, so what was I doing last time anyway? Well, what I was doing was this is the week of 9/4, and on this week I'm supposed to be talking about digital technology, and that's what I was doing. I was talking about digital technology. And digital technology is found in CO1. What does CO1 mean? It means chapter 1 of the content part of the textbook. Okay? The textbook is divided into concepts. The concepts, uh, I means issues, and S means skills. Uh, also, in this week, I want to start talking about operating systems, okay, and web research. And uh, I'm going to hand out your first assignment next week. And I may hand it out on Tuesday or I may hand it out on Thursday. Okay, but this first assignment is going to have to do somehow with using the word process, Microsoft Word or Mac Word or Google Docs Word, and uh, it's going to involve doing some research on the web as well. So that's where I am. So digital technology involves several things. It involves, uh, first of all, it's the first big topic in digital technology is data types. That is, data types that are stored on a computer. Last time I said there are elementary data types, and then there are more complex data types. But we actually got off onto talking about number systems. And we found out that I think of number systems sort of in two categories. Okay? Positional number systems and non-positional. Non-positional number systems, I mentioned Roman numerals. And I claim that positional number systems are an improvement over non-positional number systems. Why did I say that? Why did I uphold that proposition? Yes. Sorry. So you do arithmetic. In the modern age, right, we have to do lots of arithmetic, right? In all forms of business, and we have to add things, subtract things, multiply things. And it's much easier to do that in a positional number system than in a non-positional number system. Now, in the positional number systems, uh, they all have a base, okay? And what is the base? So we talked about the decimal number system, talked about the binary number system, talked about the hexadecimal number system. All of these are positional number systems, okay? So what is the base or the basis, okay, of the decimal number system? And we'll call that B, okay? So for the decimal number system, it's based on the number 10, okay? 10 is the base. Okay? In the binary number system, the base is 2. And in the hexadecimal number system, the base is 16. We will run into one other number system, as we go along. There's also the octal number system. The base of the octal number system is 8. Now, actually, there are number systems of all bases. Okay, starting at 2. There's no base equal 1, but these are always positive integers. 2 can be the base of your number system. 3 can be the base. 4 can be the base. Any positive integer above 2 equal to 2 or greater. I said last time that the decimal number system, that's the number system that we're used to using, right? That's what we've been trained in all our lives. And it's really probably the only number system any of us have ever been trained in. And the only number system we can do any arithmetic in our head. Now, in the decimal number system, in each of these number systems, there's some digits, okay? Uh, and in the base 10, they are 0, 1, 2, 3, up to 9. So there are 10, okay? The number of characters in a number system is equal to the base, okay? So if the base is 10, there are 10, you have to have 10 characters that you can write down. These 10 characters are each less than 10. They start with 0, and they go up to the base minus 1. So in binary, the characters are simply characters are just 0 and 1. In the hexadecimal number system, they are 0, 1, 2, 3, 4, dot, 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 up to 9, okay? Then 10, 10, 11, 12, 13, 14, and 15. And traditionally, we use letters. That is A, B, C, D, E, and F. Okay? That is, in the hexadecimal number system, the way to represent 10 is A. Now, sometimes they use a little a, sometimes some people use A's. Okay? It doesn't matter. The A is a 10, B is 11, C is 12, D is 13, E is 14, and F is 15. In the octal number system, um, there's H, okay? 0, 1, 2, 3, 4, 5, 6, 7. Okay? So in every case, the number of characters is equal to the base. Okay? Here there are 10 characters. Okay? Here there are 2 characters. Here there are 16 characters. Here there are 8 characters. In every case, the largest character is 1 less than the base. Here the largest character is 9, and is 1 less than 10. Here 1 is 1 less than 2. Here F, which stands for 15, is 1 less than 16. Here 7, 1 less than 8. And in every case, if you take the base, so you write numbers like this, okay? So you'll have some character, C0, okay, times the base to the 0th power, plus C1 times the base to the 1st power, plus C2 times the base squared, plus C3 times the base, okay, plus however many you need, however big the number is. So each of the C's, C sub I, is contained in the characters, okay? B is the base. B0 is equal to 1. B1 is just B. Okay? B squared is B times B. B cubed is B times B. Okay? b to the fourth power, b times b times b times b, and so forth. And this is the reason we call these positional number systems is there's a units position here. Whatever the base is position, whatever the base squared is position, the base cubed position. Okay? So let's figure out in binary. Okay, what would the binary numbers look like? Well, let's count in binary. So this is 1. This is 2. Now, why is that 2? Because it is equal to a character, 1, times 2 to the first power, plus that is a character, 0, times 2 to the 0 power. Okay? That is equal to 2 plus 0. That's 3 is 1, 1. That's 1 times first power plus 1 times 0 power. That's 2 plus 1 times 1. That's 2 plus 1. That's 3. 4, 1, 0, 0. 1 times 2 squared plus 0 times 2 to the power plus 0 times 2 to the 0 power. That's 4 plus 0 plus 0. So we can count in binary. Right? This is 1. This is 2. This is 3. 4. 5. 6. 7. This is 8. 9. 10. 11. 12. 13. 14. 15. 16. So, how many one-digit binary numbers are there? Just one. Well, we'd say 0. Starting at 0, we'd say there's 2. How many two-digit ones are there? 2. How many three-digit ones are there? 4. How many four-digit ones are there? 8. How many five-digit ones are there? 16. Now, in a computer, we store things in bytes. We talk about bits and bytes, but basically in a computer, when you put something into a computer, you can't just put in a bit. You had to put in at least a byte. A byte is 8 bits. Okay? So if we wanted to put in 0 into a computer, it actually has to be stored as 8 zeros. If you want to put a 1 into a computer, it has to be stored as 7 zeros and a 1. If you want to put in 2, like that, okay? So, what's the largest number you can store in a computer in 1 byte? Well, it'd be all ones, right? The 8 ones. What would that number be? Well, we need to learn the powers of 2. We need to learn the powers of 1. Now, anything that's a power of 2 minus 1 is all ones. Like in the decimal number system, anything that's a power of 10 minus 1 is all 9. So to store 1, you got here, to store 2, so this is 1 here. This is 2 here. How do you store 2 here? How do you store 8? I mean 4. That's 1, 2, 3, 5, 6, 7, 8. That's how you store 4. Okay. How do you store 8? How do you store 16? How do you store 32? How do you store 64? How do you store 128? So how do you store 4 minus 1? Okay, 4 minus 1 would be 3. Well, it's 1, 2, 3, 4, 5 zeros like this. Okay, then 0, 1, 1. How do you store a 7? 1, 2, 3, 4, 5 zeros. How do you store 15? 1, 2, 3, 4, 2, 3, 4. How do you store 31? 0, 0, 0, 5. How do you store 63? 0, 0, 1. How do you store 127? 0, 1. Sorry. Okay. Now, can we store 256? No. We don't have enough room. Okay. Because we only got 8 bits. Okay. We would need a ninth bit to store 256. But we can store 256 minus 1. That's 255. That's all ones. Excuse me? How am I getting all these numbers? Well, how am I getting this number right here? How did I get this number? How did I get that number? I use this formula right here. P is 2. Okay. So 2 to the 0 is, you see, this is the way we write them, but I mean, if I wanted to write this number down, I wouldn't write all this. I would just write C0, C1, C2, C3. That's all I would write down. Okay? In the positional number system, you just write down these characters. You don't actually write down the powers of the base. So this rightmost character is the base to the z is multiplied times the base to the 0 power, which is 1. This rightmost character is always multiplied by 1. This character is always multiplied by the base. In the case of binary, whatever that character is, multiplied by 2. The character can only be 0 or 1. 0 times 2 is 0. 1 times 2 is 2. Okay? What? Yeah, that's right. These number bases represent any number, integer number, okay, so far. Okay. So, you see this right here. 0 times 1. 0 times 2. 1 times 4. 0 times 8, 0 times 16, 0 times 32, 0 times 64, 0 times 128. Okay? Everything is 0 except the 4. 1, so this is 1, 2, 4, 8. Everything is 0 except the 8. So this is how you represent 8. 8. Okay? How would you represent 9? That's why I just figured stick another 1 in there. Okay? That'd make it 9. How would you represent, say, 11? 11. How would you represent 11? Yeah. 8 plus 3, right? So you see where I get these numbers from? Good. So let's work a little problem, okay? Now let's see. Last time, I'm gonna take a roll. Let's see who's not here today. So Alan, you're here again today. Let's say there were two new people here last time. Yeah, tell me your name again. There was some girl here last time, right? Okay, let's do an example then. So let me go to the second row here, okay? Uh, how would we represent the number 25 in binary? I tell you what, you get the answer there, put your hand up. Now, don't look it up on the internet, figure it out. I want you to look it up on the internet and use Google because I'm going to ask you details about it. And if you know the answer but don't know how you got it, that's going to look bad. Yes. Okay, now tell me your name there. So you're 1, 2, 3. So Martin found, okay? Martin, what are you majoring in? Biology. We got a lot of biologists in here. Are all you biologists going to be doctors and nurses? Is that it? Medical technicians? What are you going to be? Nurse? I got a bunch of people be nurses. Okay, tell me what it is. Okay, so that's 8 characters. Okay, we're gonna. So on a computer, we'd have to store these 8 characters, right? There's 8 characters. Okay. So how'd you get that, Martin? Yeah. So this would be times. This one would be multiplied by 1, right? So nothing. 2 we don't have. 4 we don't have. This one here would be multiplied by 8, right? And this one here would be multiplied by 16, right? So 16 plus 8 is 24, plus 1 is 25. That's what you do. Now let's do a further one. How would you oh, and sometimes we do write this. Write this. We write 25 to the base 10, okay, equals, and sometimes we leave the leading zeros out just between us humans, okay. Now computers never leave the leading zeros out. They always have it. They're stored 8 of them, okay. But we'll say 1, 1, 0, 0, 1 to the base 2, okay. Remember that 25 in the decimal number system, 25 in the decimal number system is the same number as a 11001 in binary. That's okay if you want to write the zeros out in front. Because the zeros out front don't do anything really. It's just that computers are sort of, the numbers are sort of a fixed length. They're not quite as flexible as humans. Humans, it's all right if the numbers are 1 digit or 2 digits or 3 digits or 4 digits. Computers don't like that. They want the digits to be 8 of them like in binary. From a mathematical point of view, yes. And, it's just that in computers, when you store 25, it takes up a whole byte. Well, I always tell the graders, we're flexible. We're very flexible. Sometimes we're so flexible. So here's a hard one. How would you do 25 in the octal number system. Whoa. I shouldn't do that. I should say 25 to the base 10 is equal to 1. Okay, in octal. Have an answer? Hold your hand up. I don't see any hands waving around. Martin, don't you have that one? You got the first one. I thought you'd be the first one to have to get this. Oh, that's not that hard. I mean, once you get the concept in your head, this is really quite easy. So the octal number system is to the base 8. It has the digits 0, 1, 2, 3, 4, 5, 6, 7. So every position has to be a 0 through a 7. First position is the units position. The second position is the third position is the 8 squared position, or the 64's position, right? The next one is 8 times 64 is 256. Yeah, right? 512. Right? Mm-hmm. What position? Well, first of all, if we're going to do this to the base 8, how many positions would it have? Okay. Would it have one position, two positions, three positions? What? This is a 1. This is an 8. This is a 64. So 25 to the base 8 would only have two positions in it. It couldn't have three positions because the first three position number in octal is 64. So in octal, 100 is 64. Yes. Yes. 3, 1. Okay. So 25 in octal is 3, 1. 3 times 8 is 24, plus 1 is 25. Okay. Now, that's really hard, okay. What would 25 be, okay? And hexadecimal. 19. 25 and next decimal would be 19 to the base 16. Okay? This would be 9 times 1 plus 1 times 16, right? 16 plus 9, 25. Let me give you even a harder one. Suppose we have 5 in hexadecimal. How much would that be in decimal? How much would 25 hexadecimal be in decimal? How would I represent that in decimal? Come on, y'all just be moving through this. Okay? 25 in hexadecimal, what is it? 2 16 plus 5. Okay? So you need to get really, really quick. I mean, this is really, you need to convince your head that this is simple stuff. Okay? And it's going to be simple, very simple, once you get it. Okay? You'll be able to do this without thinking. Okay? 2 times 16 is 32. Plus 5, plus 5, 7. This is 37. That's a 37. That's not. How much is 38 decimal? If we put it in hexadecimal, how much is 38 decimal if you express it in hexadecimal? Come on, has to be 26. See, this is one more than that, so this has to be one more than that. All this stuff we're doing really elementary arithmetic here. You know? We're doing, first grade or second grade arithmetic, binary and hexadecimal and this stuff. But now let me ask you this: how much is 38? How would you express it in binary? Well, it's got to figure out how many places it would take. Okay, this is the ones position, the twos position, the fours position, the eights position, 16, 32, 64. Okay, so it's not the 64 and 128 clearly are zero because they're bigger than 38. Okay? Now 32, if you had 32, you only need 6 more to get 38. Okay? So this is equal to 0, 0, 1, 0, 0, Now let me show you a little trick. We divide this and take 4 here and 4 here. If we know 38 in hex, the way we can convert into binary is very easy. Take the first hex digit and write it as 4 binary digits. And you take the second hex digit and write it as 4 binary digits. Hexadecimal is sort of binary shorthand. Hexadecimal is writing binary 4 characters at a time. And so usually when we talk about what's inside a computer, we say in a certain byte, we're storing these 8 binary bits, okay, zeros and ones. You don't write the zeros and ones. The decimal digits. Okay? Now, on a computer, 8-digit numbers are not very useful, right? I mean, 8 binary bits are not very useful because you can only store up to 255. So nobody wants to store such small numbers, right? So in the business world, we have to deal with larger numbers. Okay? So most computers nowadays don't store integers. Okay, as only 1 byte. They store integers as 4 bytes. Always 4 bytes. So instead of 8 zeros and ones, 32 zeros and ones. Yeah. So we'll have a low order byte here. It'll have 8 bits in it. Then we'll have the next byte, another 8 bits. Another one, okay? Altogether there's 32 bits, okay? And then here the units position will be, see here, and then the twos position, and then the fours position, okay? And over here will be, 2 to the 7th, okay? Which is 128, okay? And this will start 2 to the 8th, okay? Up to 2 to the 15th. And this will be 2 to the 16th, okay? Up to 2 to the 23rd, okay? Number 2 to the 24th, okay? Up to 2 to the 31st. So you can store numbers up to almost a 2 to the 32nd. Okay? You can actually store numbers up to 2 to the 31st minus 1. Okay? However, there's a little catch. We like to store negative numbers. Okay? So the first bit over here is usually a signed bit. And it's not 2 to the 31. Okay? A 0 means plus, and a 1 means minus. So actually, this is 2 to the 30th. So we can actually store numbers up to plus 231 minus 1, and then minus 2 to the 31 minus 1. So how big is that? To the 31 minus 1. Somebody got a calculator here, right? Calculate that for me, would you? 31st power minus 1. Yeah. Now Martin's got it again. Martin's my star student so far. Always has the answer. How much is it? 2,147,641,47. 2 billion. So basically, we can handle numbers up to plus or minus 2 billion, more or less. Yeah. There's not a 2 to the 31st power. There is a 2 to the 31st minus 1. That's the biggest number. 2 to the 31st minus 1. And that's all ones, you see. That's 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, out to 2 to the 30th. Remember, a power of 2 minus 1 is all ones, just like in decimal, right? Power of 10 minus 1 is all nines. 31st minus 1 is a power of 2 minus 1. It's all ones. Out to 2 to the 30th power. Okay? It's 2 to the 30th plus 2 to the 29th plus 2 to the 28th plus 2 to the 27th plus 2 to the 28th. 2 to the 31 minus 1. So you cannot store on the computer. Let's say you're working on a store, putting numbers in, and you got 2,247,483,648. You can't store it. You can't do it. You can't put it on the computer. Well, at least not as a standard decimal integer. You can do it, of course, because you never know when you have that number in there. But if you're dealing with, standard integer data types, you cannot put in 2,147,483,648. Because that number there happens to be 2 to the 31st power. Okay, so data types. Computer data types. So I'm going to say fixed point integers. These take 4 bytes to store. And they are in the range. I'm just going to say plus or minus 2 billion. So that's one data type. Now, the second, and these are elementary. computer data types. Now, some computers actually have what they call short integers, and those are 2 bytes long, that is 16. Okay. Now, those are in old computers, and that pretty much disappeared by now. Now, almost all the computers, in fact, I would say 41 nowadays, uh, are going to have 4 byte integers. Okay. There'll also be other like let's stick with this right now. Okay. Second elementary data type is character text. Okay, characters, and these characters are like keyboard characters, and each character is stored in 1 byte. And these characters are stored with a code. Okay. What's the code? ASCII. What does ASCII stand for? The American Standard Code for what? Information interchange. The American Standard Code for information interchange. Did you know we had a Bureau of Standards in the United States? It's, one of the bureaus of the federal government. These were the guys that bring this up. I mentioned last time that actually the industry is now more and more turning to a different code besides that different code that I talked about last time. What's Unicode? Well, it's a new code that the worldwide computer industry has developed. Okay, what's the purpose of Unicode? Well, it's to have one code for every character of every alphabet, and uh, similar to an alphabet in some cases in the world, right? And Unicode, the characters are usually 2 bytes long, 2 bytes per character. Some of them are 3 bytes per character. There's actually some that are 3 bytes per character. And I think there's some that are 4, maybe. I need to go back and check. What did we look at last time? Some of the examples we looked at last time for Unicode. What did we look at? We looked at Egyptian hieroglyphics. We looked at the Chinese characters, okay, and the Han, uh, alphabet. We looked at Arabic. Okay? We looked at Hebrew. We looked at Russian, Cyrillic. Yeah. Uh, in Unicode, is there? So Unicode has different subsets. Okay, and so if you're in some country, you don't use all Unicode. You just In the United States, we only have part of Unicode. The part that we use is called what? Latin 1. Why is it called Latin? You don't speak Latin. Why is it called Latin? The Latin part. So those were the letters, okay. The Roman. We write our alphabet with exactly the same set of characters. A, B, C, D, E. So the Western Europe, all England, France, Germany, Italy, all these countries in Western Europe use the same letters the Romans used. So if you go back and find, you go over and visit Europe and you see some ancient Roman sarcophagus or writing somehow, same letters. There's some small differences between one language and the other. Some have umlauts and wiggles things on them, but basically, it's all Latin. Latin 1. But I would say, for the most part, we're still use ASCII, okay? And then the characters are 1 byte long. And actually, ASCII's a 7-bit code. The first bit in ASCII is always a 0. Actually, if you say, well, if you write a computer program, how do you know where it's using ASCII or where it's using Latin 1? And actually, the answer to that is Latin 1 is set up so that it's like that. I forgot that. Wikipedia. Here's ASCII. How do I read it? A capital D in ASCII. How would I store a capital D in ASCII? I would store it the following way. I would store it as 4, 4. Capital D here. 2 hexadecimal characters, okay? The first hexadecimal character is along this line here. The second hexadecimal character comes down this way. A capital D, if I punch the capital D on my keyboard, it transfers into a single byte into the computer. Hexadecimal 44. Yeah. And hexadecimal 44 is what? 4, 4. And hexadecimal is equal to what in binary? Hexadecimal is just binary shorthand. Each hexadecimal character is 4 binary bits. The first 4 is 0, 1, 0, 0, 1, 2, 4, 8. The second hexadecimal character is 0, 1. That's how a capital D is actually stored inside the computer. Okay, W. W. Capital W. Now let's go to a little w. Here's a little w. And I don't want to know that's 77. Let's do this one here. Let's do a little z. A little z. How do you store a little z? A little z is stored a. A little z is stored on the computer as a7. A7 base 16. Okay. So an A is 10. The hexadecimal digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. A is 10. B is 11. C is 12. E is 13. E is 14. F is 15. 10, okay, is 8 plus 2. That's 8. And 7 is 0, 1, 1, 1. Now, I'm actually not converting, yes, I am. That's to convert A7 into decimal. What would that be in decimal? Do it in your head. Go fast. What is it? 10 times 16 is 160 plus 7. 167 in decimal. Yeah. Are there what? Letters in. Yeah. Yes. Yes. What are the characters in hexadecimal? In hexadecimal, the base of hexadecimal is 16. Okay? The characters are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. Okay? An A stands for 10, a B stands for 11, C stands for 12, D stands for 13, E stands for 15, F is 16. Okay? There's not any in G or H or I. Yes. No. No. Uh, my philosophy about memorizing is as little as possible. Again, I think memorizing is a very low level of learning, and it's better to be able to figure it out. Again. So, things like the ASCII, memorizing that's not very productive. I don't think. Um, I guess it gets to be sort of a gray area about when you're figuring something out, it's because you've memorized something. You memorize some fact, or you know some facts somehow, you figure it out. Okay. What are these things here anyway? I mean, when they have these are all on the keyboard. See, the white stuff is the stuff on the keyboard. But there's some other things besides the characters on the keyboard in this red, here. NUL, null, NOH, STX, ETX, EOT, ENQ, AK, ACK. What is all of that? These are called control characters. And when you are sending information from one computer to another, messages, okay, in a certain protocol, and these protocols have these control characters. The message EOT means end of transmission. Okay. ENQ means inquiry. It means acknowledge. Okay. NAC means not acknowledge. Okay. The bill stands for ding. Null means nothing. Anyway, all these have meanings. Okay, okay, I'm out of time there. I'm still got more to talk about in this and data types. I'm still talking about data types, and I'll be continuing to talk about data types next time. Thank you very much.